Well, this recording actually goes with all of these dates. Um, Looking at the schedule, Wednesday the 8th, there was actually a quiz scheduled for that day, so that always takes up like at least half the class, so I probably wouldn't have covered an awful lot that day. Would have covered even less on Friday because it's a holiday, and finished section 11. The reason I drew a line through the middle of that Monday class is because what I plan to do in this recording is finish section 11 and leave it at that, and I'll start section 12 in the next one. Actually, when it comes right down to it, today's date is March 26 when I'm recording this, but it seems like a good, well, in general, I like to do things with a nice long lead time. I mean, I had your final exams all written up the first day of classes. That way you're ready if something happens that makes you fall behind. You're just less ahead instead of behind. But I should probably stop babbling and set that there. So what I've already talked about in section 11 is, first of all, there was LR circuits and there was RC circuits. And then the one way of taking these things two at a time that I hadn't gotten to yet was LC circuits, a coil and a capacitor. Now, this is a little different. RC circuits and LR circuits both behave in pretty much the same way, okay? Depending on whether you're turning them off or turning them on, you get either an e to the minus x kind of thing, or the same graph flipped upside down. This circuit, on the other hand, oscillates. Instead of being an exponential function, it's like a sine or a cosine wave, okay? Before we get into any formulas, before we get into the rigorous quantitative description, let's just give a conceptual version of what's going on. So let's say that before t equals 0, this switch here is open, okay? And before t equals 0, while the switch was open, the capacitor got charged up. Somebody came along with a battery and some jumper cables and charged up the capacitor and then took the battery away. So the capacitor's sitting there all charged up, dum-da-dum, dum-da-dum, nothing much going on. And at t equals 0, somebody walks up and closes the switch. The charge then is provided with a path where the pluses can get together with the minuses, which is, of course, what they like to do. So a current will be flowing. If you're thinking in terms of conventional positive current, a current will be flowing from plus to minus, like that little tiny arrow that I drew right there. Well, so far this sounds like the same story I told for an RC circuit where the capacitor discharged through a resistor. The difference is the resistor converts the energy that used to be in this electric field into heat. And it soaks away into the environment and you never see it again. The inductor stores that energy in its magnetic field. So, well, it's a little bit of an oversimplification to say that the energy never leaves the circuit at all. The circuit will give off some electromagnetic waves, but if you're not being too precise with your words anyhow, the energy doesn't get taken away like it does from a resistor. It just gets stored up over here. And then when the capacitor is fully discharged, the circuit doesn't stop. The current doesn't stop flowing. Rather, the energy stored in this magnetic field becomes an energy source that keeps pushing the current on, keeps it flowing, okay? So at first, think of it in terms of Lenz's law. At first, when you first close the switch, the coil is going to oppose the buildup of the current. Lenz's law says that an induced EMF opposes pretty much anything that's going on. And, you know, if it's a nice day, it wants rain. If it's a rainy day, it wants sun. Some people are just never satisfied. So if the current is building up, the coil tries to hold it back because, you know, it's pulling energy out of the circuit to build up the magnetic field, and that creates an opposing voltage. But once the current peaks out and it starts going down again, then Lenz's law opposes the decrease, and it keeps shooting current through the wires after the capacitor has long since quit pushing on it. This recharges the capacitor the other way around. By the time the coil finally runs out of magnetic energy, the capacitor has been recharged back up to the same voltage that it had in the beginning. It's just charged the other way around now, positive on the bottom this time. Well, the pluses and the minuses kind of look at each other and say, well, let's try this again. And so, you know, opposites still attract. They try to do it again, and a current starts flowing back around the circuit the other way. Once again, the inductor makes it overshoot until the capacitor is recharged. We're back to the first picture now, and the cycle repeats over and over and over again. So that's what's going on in words. If you want to think of it in terms of conservation of energy, if it's a circuit that truly has no resistance, so that which would be kind of like having a frictionless mechanical system. It's kind of an idealization, but it can be a decent approximation if you don't watch it for too long. If the circuit has no resistance, the energy just goes back and forth. The energy of the electric field, remember that's what the previous page was about, was the energy stored in the fields. The energy in the electric field moves over to become magnetic energy, goes back and becomes electric energy, becomes magnetic, becomes electric, and it just keeps switching form back and forth over and over again. And without any friction to convert it into heat, the oscillations would persist, well, maybe not forever, but they'd be very persistent. So that's the qualitative picture. The charges move back and forth, kind of like in physics 131, I talked about a mass bouncing up and down on the end of a spring, okay, a harmonic oscillator. If there is friction, that acts, well, an oscillator that vibrates forever would be simple harmonic motion. If you add friction, then you have damped harmonic motion where the amplitude tapers off with time. And that's very much like what would happen here. Resistance is to the mechanical system, or resistance is to the electrical system, what friction would be to the mechanical system. And let's see, here's the part where I talked about the energy. I already said that. The total energy in the system would be the capacitor's energy plus, should probably get that centered a little better, the capacitor's energy plus the inductor's energy, which from the previous page, 1/2 CV squared is what's in the capacitor, 1/2 Li squared is what's stored in the inductor. Add the two of them together, that's the total energy stored in this circuit. And you could use this to solve conservation of energy type problems, similar to those that I threw at you in physics 131 for a mechanical oscillator. When the current is zero, which happens only for an instant, but at that instant, that's when the voltage on the capacitor would be at a maximum. All of the energy is in the 1/2 CV squared term then. And likewise, a quarter of a cycle later, when the voltage hits zero, when this term is zero, all of the energy would be in the coil when the current is at a maximum. So I could ask you questions like, well, you know, if the maximum current is this, then what's the maximum voltage on the capacitor going to be? And that would be a pretty straightforward thing to do with conservation of energy. I could ask you questions like that, but I'm not going to, because I packed a lot of stuff into section 11, and you know, you can only assign so many questions. Well, I suppose I could assign, you know, 250 problems for homework, but I try to be somewhat reasonable. So anyhow, I'm not going to take the space in the assignment to ask anything like that. But now comes the quantitative, mathematical description of what's going on. Maybe I'll start a clean page for that. Okay, so here's our circuit again. Got a capacitor, and we've got an inductor, and capacitance C, inductance L. Oh, let's make this like the first picture in the note packet, where it's positively charged on the top, negatively charged on the bottom, and then this would be the positive side of the inductor, and this would be the negative side of the inductor. And just like when I wrote the differential equation for the LR circuit, we'll start with the loop rule. So if you start here and see, what did I do? Actually, I think I started up here and went around this way, counterclockwise. So we went from the high side to the low side of the capacitor, minus 1 over C times Q. That's the voltage across the, this is from the definition of capacitance. C equals Q over delta V, can be rearranged into delta V equals Q over C, which is what I used for the voltage across the capacitor. So you got that, and then you go across the inductor from low to high, which is why I've got a plus sign there, but the voltage across an inductor is minus L di dt, and that gets us back to our starting point. So here's the differential equation that governs this circuit. And somebody out there is going, oh no, not another differential equation, but hey, you know, that's life. Get right back to you. Well, you have to have everything in terms of the same variable before you can integrate. I mean, we've got a Q here, but we've got an I here. We need another substitution. So I'm just going to recopy the first term. Well, actually, before I do that, I'm going to cross, you know, the minus signs cancel. Maybe I should have just gone around the circuit in the other direction in the first place, but 1 over C times Q plus L, the self-inductance of the coil. My substitution is the definition of electric current. As you all are supposed to have faithfully memorized, I is the derivative of Q. It's the rate that the charge changes. The charge on the capacitor would be one, well, the charge passing by some point on the wire, or the, anyhow, I equals dq dt. So that means what we have here is the second derivative of the charge. There's kind of a standard form for this equation. I'm going to move a few things around to get it into that. So one thing people like to do is group all the constants together. Hold on. People are sending me texts. So usually what you do with a differential equation is put the terms in descending order, like the highest order derivative, then the next highest one, and so like a third derivative, then a second derivative, then a first derivative. And if you had all those terms, that would be a really tricky thing to solve. But divide both sides by L in order to collect the constants together. That's the other conventional thing to do. And what you're left with is that plus that. So put this term over here, put that term over there, and divided by L. And now, when I took differential equations, they taught us all, one more time. When I took differential equations, they taught us all different methods for solving. There's integrating factors, and there's Laplace transforms, and there's all kinds of tricks that you can use for different situations. But once I got beyond that and started taking a whole bunch of physics courses, usually, all those other things have their place, but it seemed like usually it was one of two things was how you solved the differential equation. One was to say that whatever function was the answer equals some infinite series, and then you look at the infinite series and you say, oh, well, all those higher order terms are so small, I can just ignore them, and you stick it in and reduce it to a polynomial that way. And the other one that comes up very often, actually, is you just look at the equation and say, oh, that's the harmonic oscillator equation. Everybody knows the solution to the harmonic oscillator equation, and that's what's going on here. The way to solve this is to look at it and say that's the harmonic oscillator equation, and let's review harmonic oscillators. Okay, so from Physics 131. The system we were considering then was a spring with stiffness constant K. K is the constant from Hooke's law. You've got a mass M, which has been displaced a distance x from equilibrium. And this is a frictionless surface that it's sliding back and forth on. Otherwise, it becomes a more complicated equation. But Newton's second law says F equals ma. And if you dig out your old notes, all of this should be in there. This is actually kind of a review thing. The force pulling on this mass, the restoring force from the spring, is the Hooke's law force, minus k times x, equals the definition of acceleration is the second derivative of the position, x. And if you rearrange things a little bit, divide both sides by m and put the differentials in descending order again, like I was saying, you get this. Where this coefficient in front of the x term is usually set equal to omega squared, where Omega turns out to be equal to 2 pi f. Omega is the frequency in radians per second. F is the frequency in cycles per second. But anyhow, it's the same equation. It's just here, I'm calling my variable q. Here, I'm calling my variable x. Here, the constant coefficient is this. Here, the coefficient is, but in both cases, it's the second derivative plus some constant times the variable itself equals 0. It's the same equation, so it has the same solution. Same equation, has the same solution, and last fall, when it was x, that was that the position of the mass is equal to a cosine of omega t plus some phase angle that we were representing with the Greek letter phi. Other textbooks sometimes use delta, where, you know, omega was the square root of k over m. Well, omega squared now is this coefficient here, 1 over LC. So all I'm going to do is write the same solution, just calling it q instead of x. So q equals, let's call the amplitude q max, maximum charge on the capacitor. And like I said, the coefficient of this term here is omega squared. So over here, omega squared would be 1 over LC. So omega, you know, take the square root. Omega is 1 over the square root of LC, where, again, omega equals 2 pi f. So it's the electrical counterpart of a harmonic oscillator. It's the exact same behavior, just, well, like I said earlier, it's the same story being read. You're just sitting in a different place as you read it. Okay, the charge inside these wires goes back and forth over and over again, the same way this mass goes back and forth over and over again, and it's just the same thing. So like it says here, it's the same thing I said when I was talking about an RC circuit. All I put on the formula sheet was the formula for the charge as a function of time. Well, if a question asks you about the current, take the derivative. You're supposed to know that I is dq dt. If the question asks you about the voltage, well, voltage across the capacitor is going to be the same thing as the voltage across the coil, because those are the only two things along this loop. So, you know, if this is 3 volts, that's got to be 3 volts, because there isn't any place else for there to be a potential difference. So voltage across the capacitor, voltage across the coil, whatever you're interested in, you take the definition of capacitance and rearrange it into delta V equals Q over C, and that's how you can get the voltage. So I'm going to do this example, and then that finishes off section 11, and that's where I'll hit pause for a little. Well, that's where I'll end this recording and probably do one more this afternoon. Okay, so here is the same picture that was at the top of the page, except specific numbers have been filled in for the capacitance and the inductance. And it looks like, I really wish I could get a sharper focus on this, but well, we'll try and put it in a nice, look at it in a positive way. It's a soft focus. It's supposed to make this all look romantic. Let's just think of it that way. Anyhow, I think you can read that. It says 20 microfarads, and this over here is 32 millihenries. And initially, there's 20 volts on the capacitor. You close the switch at t equals 0. Closing the switch at t equals 0 gets rid of the phase angle, as opposed to, if you close the switch at some other time. And, well, the first thing it asks for is the period. So maybe I should have kept this handy. My plan of attack for getting the period is that I can get the frequency from the square root of, 1 over square root of LC. And then the period is going to be the reciprocal of that. So that's kind of the summary in 25 words or less. Details go like this. Part A, omega equals 1 over the square root of LC. And I've got numbers for both of those things. They were on the picture. Inductance converted into henries is 0.032. And 20 microfarads, 2 times 10 to the negative fifth. In other words, 20 times 10 to the negative 6, 20 microfarads. Calculate, and I'm gonna write this down because I'm going to need omega again in a later step. So there's the so-called angular frequency, the frequency in radians per second. Question asks for the period. Of course, one thing to avoid is you don't want to get omega mixed up with F. I think I saw somebody do that on a paper I graded this morning. One of those if I had a nickel kind of things. So it's not just 1 over 1250, rather it's 2 pi over omega, from the fact that omega equals 2 pi f, divide both sides by f and divide both sides by omega, and it follows that 1 over f, maybe I should write it down. Well, no, I already did. It's right there. Divide both sides by f, divide both sides by omega, and you got that. So 2 pi over the 1250, and the period is just a little more than 5 milliseconds. Part B, the voltage across the capacitor at t equals 7 milliseconds. So, like I was kind of saying earlier, you look at the formula sheet, all that's on there is a formula for the charge. You have to put that together with the idea that current is dq dt. So that's what did I do? Oh, it's over here. Too many pieces of paper. This is Q, what I came up with a few minutes ago. So the derivative of Q max cosine of omega t plus the phase angle. And as I said, the phase angle is going to be 0 because the switch was closed at t equals 0. Okay, if the switch is closed at t equals 0, that means the charge was at its maximum at t equals 0, because charge would be at its maximum when you close the switch. So let's just get rid of the phase angle right now. So as far as taking the derivative of that, it's going to be, well, Q max is a constant, and derivative of cosine is minus sine, but there's also going to be, well, I might as well write that much of it down, minus sine of omega t. So derivative of cosine is minus sine, but there's also a factor of omega because of the chain rule. You have to take the derivative of what's outside the parentheses, which is the derivative of cosine, times the derivative of what's inside the parentheses, which would be the derivative of omega t. Omega is just a constant, but the derivative of t would be t to the 0 power. So the current as a function of time is going to be minus omega Q max sine of omega t. Just tidying things up a little bit, putting all the constants together and so on. I've got a number to fill in for omega. That was the 1250 up here. The maximum charge. Well, the question told me the maximum voltage. So since C equals Q over delta V, that tells me, well, first of all, it tells me in general that Q equals C times delta V. And in particular, if it's the maximum you're interested in, maximum voltage corresponds to maximum charge, and the capacitance C is, I think, yeah, I already used that number up here once, 2 times 10 to the negative 5th. The maximum voltage is 20 volts, and that's going to be 4 times 10 to the negative 4 of a coulomb. So now filling everything in, 1250 for omega, 400 microcoulombs for Q max, omega 1250 again, and it asks what is the voltage at 7 milliseconds. In other words, this is radians per second, so I've got to have seconds to go along with that. You've got to match. And this is going to be 8.75 radians, not 8.75 degrees. Nobody did that this morning because I didn't ask a question this morning where that came up. But if I had, I'm sure there would have been somebody who punched up the sign of 8.75 degrees instead of 8.75 radians. So that times that times that, negative, the minus sign just refers to which way the current is flowing at the moment. Half the time it flows one way, half the time it flows the other way. Right now it's going in the, would it be the opposite direction of how it started out? It doesn't matter. It's 0.312 amps. Oh, that's part C. Find the voltage. Okay, I kind of skipped ahead. I'm sure you spent the last 10 minutes sitting there going, what is he doing? Sorry about that. That's part C, find the current. I just glanced at the question, and let's do part B while we're at it. Since, no wonder I was having a little trouble following my notes. Maybe I should recopy those. They're a little messy. Delta V, again, from the definition of capacitance, if I solve this for delta V, it's Q over C. And so that would be this expression for the charge. Q max over C would be the maximum voltage. Any voltage is equal to the corresponding charge divided by the capacitance, and that includes the maximum voltage, or the maximum charge, which would correspond to the maximum voltage. So maybe I should point something out here. This will become significant when we get into section 12, which is about alternating currents, which is what we're dealing with here at the moment. Notice that the current is a sine, but the voltage is a cosine, okay? Current and voltage do not need to rise and fall together. Rather, in this case here, you can see they're 90 degrees out of phase with each other. If the current, actually it's an upside down sign because of the minus sign. If the current is a sine, the voltage is a cosine, you've got them a quarter of a cycle out of phase with each other. But that's a topic for the next unit. All we need to do to finish this one off is fill in some numbers here. So delta V max. No, that's the 20 volts that was given in the question. Of course, omega t is still equal to the same omega t that we had over here, 8.75 radians. And so you punch that up, and negative 15.6 volts. Okay, so actually that should be up there, and this should be down there. And if I was a really slick video producer, I'd do this over and edit the thing, and yeah, you'll figure it out. ACB. think that's probably clear enough. And I should probably just repeat that an alternate approach for the same problem, I'm not going to write out the details, but if it appeals to anybody, you could have done it this way. You could have done it with conservation of energy instead. Might have actually been a little quicker. I'd have to write it out, but maybe I don't need to write anymore. It's all here. But from knowing the maximum voltage, and from knowing the voltage at the time, after you've done part B, you could get part C out of this, okay? Because Vmax here, that's the 20 volts given in the question. And the delta V at the moment you're interested in is the negative 15.6 volts. That was the answer to part B. So you could have solved for I. To do part C, you could have just solved for I out of, this is equal to that, conservation of energy. And actually, that looks like it would probably have been shorter than the way I actually did it here. So, as with many kinds of problems, there are alternatives. Sometimes one alternative is easier, sometimes another one is. That brings us to section 12, which will be the next video. I can hardly wait.